Okay, so I guess it's time to start. The data from the test was interesting. Um, this is kind of what it looked like in blue. So there was a sharp spike on the really far end, and then there was a really broad distribution kind of encompassing the upper part. And the way I design it to be is with the curve being about maxing at 70. So 70 is the B minus C plus range. So, and there were, I mean, if you take away this crowd, then I mean, the class is kind of looking like the red one, but it's a little bit more broad. I mean, what does that mean statistically? It just means that there's well, it's a long standard deviation. So, so what am I doing? Thinking about things. From the polls, it looks like the best time for people to have a problem session. Problem session is optional. That would be Wednesday afternoons. So that was, but I'll send emails that I was going to confer with people a little bit more. Also, so what's going on? Some people didn't take the test, and I put them in the testing. I put their tests in the testing center, and I wait until Wednesday, and then I'll take theirs and grade it. And then after that, I'll give you back. So a week from today, I'll give everyone back his or her test, and also I'll post an answer key, so that way you can see the work and then what's done. And also the answer key, that way you guys can look and see what you've done wrong, what you need to work on. And then I'm going to put a retest in the testing center that it's optional as well. But that way you can see, so you can work towards, okay, so I'm weak here, I need to study this, and then hopefully correct that. And I think you have the rest of the month, so you'll have enough time if I mean, not that I want anyone to drop, but if it's just not sticking at all, if you want to reach it before the drop deadline, because that way it can get uncomfortable if you're just completely not getting it, and then and that's okay. That's called the underprepared student if you're not prepared for the class. And this is in this class. So this is one of the classes that people hate. So it's about one quarter of all college students attempt this class sometime in their career, and about a third of those students fail it. So it's the fail rate for this class, and it's been that way since 1960. Okay, so that's people haven't changed. I mean, if you think, okay, actually, in a way, humans are actually kind of getting dumber. Not necessarily in chemistry, but we're getting bad at surviving. So, our brains are actually shrinking. And what's shrinking is not necessarily our intelligence. Our intelligence has been the same for the past, 200,000-ish years. But it's our survival skills. I mean, if you stuck me out in the woods for a couple of weeks, I'd be dead. I couldn't make it. So, but, stick me in Costco, I can live forever. Right? So, but I mean, we're not any better, we're not any smarter now than we were in the 1920s or the 1960s or 20 years ago, and the averages seem to pan out. If it makes you feel better, physics is worse. So physics, general physics, the calculus-based physics, half students fail that class. So our physics 170 or equivalent. The 50% of students don't pass that. And same thing with developmental math. So whatever the entry-level math class, half the people failed. So that's kind of, that's, well, I don't know, that's the entry-level math, that's the state of Hawaii. I don't know about the rest of the country, but chemistry basically is a third. Well, it's a half if you count people that drop. So actually the numbers are actually slightly inflated. So UH Manoa, for instance, their not pass rate, their fail rate is 1/3. Their not pass rate is somewhere around 45 to 50% because of students that drop. So, but I want to work with you guys though. The average this time was a little low, and I think it's for two reasons. It was the spike around the low scores, which carried the averages down low. I mean, there were quite a few students that had 25% as the test score. And of course, with a multiple choice test of 5 answers and one was given to you, that's essentially chance. One student got a 20, that was a low score, and then there are 3 or 4 that had 25. So which means that that score was actually probability only driven scores. So, and those are the students I'm really concerned about. But I mean, the other thing to note, this is a long semester, so which means you can pull it all together. I mean, this is in the summer session where it's 6 weeks long. This is a 15-week course, and some people just don't get it till the end. I mean, I've seen students that get D's and C's and then hit the final and they get an A. So that on average, about 10% of my students score higher on the final than on the tests. So, okay. Anybody have any questions about what's going on then? Unfortunately, we can't brood on this too long because we have almost 2/3 of the material to cover. So.
What is the deadline to complete the retest?
I haven't said it yet.
Okay.
I'll probably do it by the drop ad or around the drop ad date because that way then I have to look it up again. So that way students will have options.
I think it's like November 4th or something like that.
Okay.
I'm not sure.
Okay.
Anyway.
Then I'll probably make it that date unless there's just so that students can have feedback, or maybe a day or two before, so that way I can get the scores out to people. Okay. So where were we before we talked about the tests and whatnot? We're talking about gases. So we're in the gas laws, and especially the ideal gas law. And now I'm going to move on and talk about partial pressures. So ideal gases. So we're going to talk a little bit more about ideal gases. We might get into this class. We'll see. But ideal gas is a perfect gas. It's something that doesn't exist. And what is a perfect gas? A perfect gas has no interactions with each other. So since there's no interactions with each other, then if you have a mixture of gases, you can do what's called Dalton's law of partial pressures. So meaning, if I put an atmosphere of carbon dioxide in a cylinder, then I had an atmosphere of oxygen, then I had an atmosphere of nitrogen, then those pressures just add together. So, which is mostly true. So, especially at high temperature and pressure. And this is also where, I don't know why Trove does it this way. Everywhere else, the mole fraction for gases is Y. Typically speaking, when you see X, that's typically the mole fraction for liquid. Meaning there's a series of laws. Have you ever heard of the Code of Federal Regulations, the CFRs? No, you haven't. Okay, so there is a bunch of laws, and they would fit probably something on the order of 3 to 5 times the size of this room of books. And they're called the Code of Federal Regulations. They're laws. Okay, there's laws, there's labeling laws, how big to make the font on the label for things, for nutritional laws. There's the law for chemistry labs is 23 CFR 1910. That's the 23rd book of the Code of Federal Regulations, law number 1910. So, meaning there's 1,000 other laws in the 23rd. There's at least 2,000 laws in the 23rd book of the Code of Federal Regulations. There's a subset of that called RCRA. I forget which CFR it is, but RCRA deals with emission standards. And there's a bunch of laws saying, okay, this is how much you're allowed to pollute. And those laws have equations in them, and those equations have Y instead of X. And if you take an engineering class, and they talk about mole fractions in the gas phase, they use Y. So if you're ever somewhere, if you're looking at law books, or if you're doing work on anything and you see a Y, it means mole fraction in the gas phase. Well, okay. So at least when it corresponds to an equation. So mole fraction is just the number of moles, Na, that's the number of moles of species A over the total number of moles. So that means if I have 100 moles of something and then I have 70 moles of water over 100 total moles, that's a 0.7 XA. So that's the 70 over 100, 0.7. And since pressure and number of moles is directly proportional, you can get the mole fraction by just the fraction of the pressures. Okay, so give you an example of the problem. In a 1 liter container, a mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 Kelvin, 25 degrees Celsius. If the partial pressure of helium is 341, the partial pressure of neon is 112, what mass of argon is in this mixture? Okay, so here is the digested things. We have a container that's 1 liter, and it's at 298 Kelvin. The total pressure, PT, total pressure is 662 millimeters of mercury. The helium pressure is 341. The neon pressure is 112. We need to know the mass of argon. So first of all, we need to know the pressure of argon. How do we figure this out? The pressure of argon, this is going to be equal to the total pressure, 662, minus the pressure of helium, 341, minus the pressure of neon, 112. So what is that? So 662 minus 341 minus 112, that's 209. So that equals 209 millimeters of mercury. Okay, so now we need to know, so what? So we need the mass of argon. So one of the ways we can figure that out, we need the moles of argon, and then the moles of argon times 40 grams per mole. That will equal the mass of argon. So that's a G. And where am I getting 40 from? Periodic table. I think argon's 40. 39.95. Okay. So ideal gas law, PV equals nRT. N equals PV over RT. We already know the pressure, 209 millimeters of mercury times atmosphere to 760 millimeters of mercury. Volume is 1 liter. R is 0.08206. Liter atmosphere mole Kelvin, 298 Kelvin. And what is this? 209 divided by 760 divided by 0.08206 divided by 298. And this equals 0.0112 moles argon. Then we have 0.0112 moles argon times 39.95 grams argon per mole argon. And this equals 39.95. This is 0.449 grams of argon. Okay. So, recap for this one. We have a vessel that's 1 liter, 298 Kelvin, total pressure is 662 millimeters of mercury. We know that there's 341 millimeters of mercury of helium, 112 millimeters of mercury of neon, and then what is the pressure of argon, or not, what is the mass of argon? So we take the total pressure minus the pressure of the other two gases to get the pressure of argon, and then ideal gas law to figure out the moles of argon, periodic table, figure out the mass of argon, which is about 0.0449 grams of argon. Questions with how to do this one? You're like, why do we care? What's the big deal? Why do we care about argon in the system? Air is about 0.9% argon, depending on dry air at least. So I mean, air usually has humidity in it. There's not, unless you're in like Antarctica, there's going to be a little bit of water vapor in the air. And if you have a system that you recycle everything, that's one of the problems about having the Earth atmosphere, is that we can't really recycle everything. There's systems, and we have to purge the system. So have you ever driven by a distillation column before? Especially the ones that are not in California. California, they've got pretty strict laws. But if you drive by Gary, Indiana, or if you drive by Toronto in Canada, you see flames. They have flames shooting out from it looks like, you feel like you're in hell, because it smells like sulfur and there's flames shooting out from places. So, like, why are they doing that? Why are they purging the system? And the answer is because of argon. Because air is typically an intake for things. And what they found out, well, okay, we want to be environmentally conscious. We want to recycle as much as we can. So let's just recycle everything. And if you have something as air as an input, and then you recycle it back into your system, what happens is that the stuff that can be recycled reacts, but then argon doesn't react. But it gets cycled again, and the reactants and products go away, but the argon accumulates. Eventually, you just have a reaction vessel full of argon, and that does absolutely nothing. So because of that, we have to purge the system to get rid of the argon gas. And you see that for a lot of industrial processes. If you're wondering, like, well, why don't we just recycle everything? Well, it's unfortunately because there's argon in air.
Excuse me.
Yeah.
Nothing personal. I'm just having trouble deciphering some of the letters.
Which one?
What is the N? What does the N stand for?
That's the number of moles.
Number of moles in argon at the beginning? In the red?
In the red. Yes.
That's number of moles?
Yeah, N argon.
Okay.
Yeah.
And the PR, is that PV or?
PV equals nRT.
Thank you.
That's the ideal gas law.
nRT. I'm still stuck on chapter 4. I'm not here yet.
Okay. And solving for N, PV over RT.
Thanks.
That's you. Anything else that's not clear? Okay. All right, and what I just mentioned, argon is that, and that's a problem because it accumulates. And for those of you that are scuba divers, and actually there's some issues with scuba diving coming up because helium has become an endangered element. So we in the United States we stockpiled helium right around World War I, because we used it to make blimps or zeppelins if you're in Europe, and the blimps were used militarily. They're a way to get rid of U-boats. So that they would have blimps follow flotillas of ships, and if a U-boat came and used torpedoes to sink the ships, the blimp would float over the U-boat and wait till the U-boat surfaced, and then they would drop bombs on it and sink it. So, of course, the old U-boats, they would have diesel engines. Now, of course, submarines are nuclear powered, so they don't really have to come up for, basically they come up when they run out of food. So, so what we did in the United States, we stockpiled helium. And then Congress said, why do we have to stockpile helium? Get rid of it. So helium's really cheap right now, but it's about to run out. And that's a problem because because of this, so because of oxygen. So if you're scuba diving, so I've never scuba dived. I haven't scuba dived before, but well, if you are here, so if you're at the surface, your pressure is 1 atmosphere and oxygen concentration is 20%. But if you dive down 30 meters, so 10 meters of water, this is 100 feet, you have a total pressure of 4 atmospheres, 1 from the atmosphere, 3 from the water. The partial pressure of oxygen in your lungs is about 84% of an atmosphere. And the problem with this is that oxygen can kill you. So it's the old moderation argument. So oxygen, like too much of a good thing will kill you. Oxygen is included. So we are okay at sea level. So that doesn't bother us. And I'm prone to altitude sickness. And if I go up, I mean, anything, I can start to feel it as low as 6,000 feet, but definitely at 8,000 feet, I feel the altitude. And 10,000 feet, I'm a very unhappy camper. But and most humans feel this way though, at about 70% less than this. So, but we can breathe pure oxygen at this pressure, and but the thing is, if you are scuba diving and you go further, you can get to the level of oxygen toxicity. So I know what hypoxia feels like. You feel kind of dizzy. Your heart goes really fast. It feels like I got cotton in my head. So that's myself. I've never been super oxygen enriched. Apparently your heart beats really fast and you don't breathe as much. So like now you're like, then you have to breathe for like 2 minutes. So it's got to be a really weird feeling. But I guess that's what it's like to have a lot of oxygen in you. But the way they get around this scuba diving is they do a mixture of helium and oxygen called heliox, and they drop the oxygen concentration. So then you switch tanks. So if you're going down and you switch tanks and you have just lower levels of oxygen, so that way the pressure, you'll still be in this range here and not get to the oxygen toxicity level. Another thing with this is also one of the secrets that, I mean, it's not a secret anymore. This is one of the ways that the United States made it to the moon and Russia didn't. United States, one of the things that we did, we had our astronauts breathe pure oxygen, but they breathed it at a lower concentration. So they were breathing pure oxygen at around 15% of an atmosphere. So, I mean, can you imagine? That's got to be, I mean, now also in the International Space Station, I think they breathe air. So the cosmonauts, they breathe air. They put air on their capsules and their attempts, and there was too much mass. They didn't make it all the way to the moon. But we did. Like I said, we just used pure oxygen, but we lowered the pressure. So that's got to be a scary job. Whew. Breathing thin air that's pure oxygen in the middle of space. It takes 4 days to get to the moon too. Whew. I kind of dream about being an astronaut, but I don't know. It's being a bomb. Breathing thin air. All right, so, but hopefully you can follow this one. Air is 78% nitrogen. What is the partial pressure of nitrogen on 1 atmosphere? How many people think it's A? It's 0.78. How many think B? How many think C? How many think you can't tell? I've got a few people voting for A. I was trying to make this an easy question. Is your confidence just shattered? It's 0.78. Because partial pressure laws and mole fraction. So if you're at 1 atmosphere and 78%, that's 0.78 times 1. It's 0.78 atmospheres. So this also goes with scuba diving. 2 other dangers of scuba diving. Like I said, I've never done this, but one of them is nitrogen narcosis. So I guess I call it narked. You get narked if you go down low. If you go down low, you can get the concentration of nitrogen in your blood gets so high that it acts like an opiate, and you get high. And I guess, but that sounds like fun. But I mean, if you're underwater welding and suddenly you're high, you start giggling and you have a torch, that can be a problem. The other thing is with nitrogen in your blood, if you ascend too quickly, so if you're under pressure and you ascend too quickly, you can get a condition called the bends, where the nitrogen bubbles boil in your blood and you bend over. It's the discovery of that was actually not from scuba diving, it was from the Brooklyn Bridge. So when they construct the Brooklyn Bridge, they had workers go underground and underwater, and they're in a lot of pressure. And another thing I would not want to be is a miner or something like that. I mean, there's these people, they're working their shift, and they're underground, underwater, and they're working. And when you're done with your shift, you're like, get me the heck out of here, right? You're gonna, like, you want to be in an elevator. You want to leave as fast as you can if you're working underneath the Hudson River, right? So what do? These workers, they were working underneath the Hudson River. They came in the elevator, like, oh, fresh air, like, oh, and they bend over, like, oh, what's wrong with Smith over there? Like, oh, he's got the bends. It's called the bends because you bend over because it hurts because the bubbles also go in your joints and it hurts to move. You're like, move your arm. No, it feels good here. Stand up. Oh, it hurts. It's called the bends because you bend over. So what's the solution? You ascend slowly. So it's going to be a tough sell for those workers, but I mean, it works. Also, shouldn't scuba dive before you go on an airplane. For that reason. Okay. So, changing topics yet again. But any questions before we move on? Okay. So, next thing I'm going to talk about is vapor pressure. And the idea with vapor pressure, so here, let me explain this apparatus. We're generating hydrogen. You put zinc and hydrochloric acid, and then this generates hydrogen gas. And then we bubble it over, and we collect the hydrogen gas in here. So the hydrogen bubbles through, and you have this container. This is water. And then then this fills up with hydrogen gas. But also in this mixture, although this right here is hydrogen, this has got water in it as well. Where does the water come from? It comes from the liquid. And this idea, we call it the vapor pressure. So what it is really, so the actual reason for this is, so temperature means average kinetic energy. This is temperature, and if you look at kinetic energy, so this is what a temperature energy plot looks like. So we'll talk about this soon. But actually, I guess I gotta wait. Kinetic energy, no, I should do it this other way. Kinetic energy, not temperature. This is gonna be number. At a given temperature, there's the number of gas particles. It's a distribution, and if this is the heat of vaporization. So heat of vaporization, that's the amount of energy it takes to rip the gas from the liquid to the gas phase. So the reason why, so here's solid, so this is water. Here's solid water. Here's low temperature. High temperature, start moving. Gets hot enough. Now it melts. This is a liquid. It has energy. It gets faster. It flies apart. Now this is a gas. Okay, so the states of matter directly deal with the attraction between the molecules. And temperature is average kinetic energy, but average means that everything's not the average. There's a distribution, and there's a slight distribution that has enough energy to rip out of the gas of the liquid phase, the vapor phase. And if you increase the temperature, so let me increase the temperature, do green. Oh, no, that's a low. I'm sorry, that'd be a low temperature. That's a low temperature. I'll do pink. This is a high temperature. So the broad one is the high temperature. The green one is the low temperature. The low temperature has a smaller fraction. The high temperature has a higher fraction. So the higher the temperature, the more vapor you're going to find over a liquid. And that's the real reason why it happens. But the way we model it is we say, okay, there's a pressure. That the vapor pressure is the pressure that the liquid puts on the surface. It's not really what happens, but it works as far as a model. And the other thing with the vapor pressure, if the ambient pressure equals the vapor pressure, the liquid boils. So, which means that the vapor pressure of water is at 100 degrees Celsius is 1 atmosphere. So that's why water boils at 1 atmosphere. If you decrease the pressure, the ambient pressure, water boils at a lower temperature. If you increase the pressure, water boils at a higher temperature. That's the idea behind a pressure cooker. So pressure cooker, if you ever had a pressure cooker, at the end you turn the valve, steam comes out, right? Because you're under pressure, which means water has a higher boiling point. And the higher boiling point means more energy hits the food that you're cooking. So kind of like, and why do we care about that? Well, we talked about before about gases. So gases are pretty diffuse. That so gas versus water or air versus water, there's about 1,000 times less matter in air than there is in water. So let's compare that to cooking. So if you cook a turkey in the oven, how long does it take? 4 hours, depending how big your turkey is, right? How long does it take in hot oil? Not long, 20 minutes, right? Why is it so much faster in hot oil? And the hot oil isn't even as hot as the oven. It's because more matter, more collisions, more energy transfer. But anyways, so back to liquids here. So or back to gases. So we have the vapor pressure, and like I said, where it really comes from is the fraction of gas due to temperature. But you can determine it directly by the temperature that things boil at. So for instance, here is the vapor pressure of water versus temperature. And we have it tabulated for you right here. And the next problem, we have to use the 17.55. This is something that you're not going to ever have to memorize. So this will always be given to you. Another thing, if you ever had freeze-dried coffee or something like that, or so instant coffee, I shouldn't say freeze-dried, just instant coffee. The way that they make instant coffee now is that you make coffee and you draw a vacuum, and then the water boils away and you're left with the powdered coffee. So they used to do it by boiling it, but then I don't drink coffee, but I guess it makes it taste burnt. I don't know. So if you have a coffee you heat it too long, it tastes burnt. So that was the old instant coffee. Now the newer, improved instant coffee since like 1960 is from drawing the vacuum. So instant coffee is old technology, of course. Okay. So let's use this for an example. In order to determine the rate of photosynthesis, so the oxygen gas emitted from an aquatic plant is collected over water at a temperature of 293 Kelvin and a total pressure of 752.2 millimeters of mercury. Over a specific time period, a total of 1.02 liters of gas is collected. What is the mass of oxygen in grams from that? Okay, I guess I should explain why do we keep on using millimeters of mercury. So if you're wondering, the way that we take nowadays we have pressure sensors that just outright give the pressure. But an older kind of archaic pressure sensor, so you have your reaction vessel. You have your reaction vessel, and attached to that is something that we called a U-tube apparatus. You'll never guess why this is called a U-tube apparatus. So you have a U-tube apparatus, and in this, you have mercury. So you have mercury sitting in the bottom of that U-tube. And then the idea, so right now, the ambient pressure is the same as the pressure inside the container. So let's say we draw a vacuum. So if we draw a vacuum, what's going to happen is, oh shoot, I might have to erase the pressure here is going to go higher. Let me think. No, the pressure. So then, if you draw a vacuum, the mercury is going to be pushed from here, and the mercury is going to go up the tube, and then this distance here. You could take the difference in the. So if you have a U-tube, and then you have mercury in it, you could take a meter stick and then just measure the millimeters of mercury from that. And that's why we say there's a lot of times millimeters of mercury. It was literally you had a glass U-tube, so glass is clear, you can see through it, and then you just take a meter stick and you find the height of mercury, and that was your pressure, or at least your pressure relative to atmospheric pressure. So you had a barometer, and you had a meter stick, and those two would tell you what because you could take from the barometer is the pressure of the atmosphere, then comparing it to the pressure inside the chamber. So if you're wondering why we keep on using millimeters of mercury, it's because it used to be an easy way to find pressure. Now, of course, we have electronic probes that tell us everything to several thousand decimal points. Okay. So this problem, here's my beautiful artisticness, and here we have a vessel. We have a water bath, and in this vessel we have algae. Like my algae, it looks like green spaghetti. Here's my green spaghetti, and this is in water, and this is reacting. As it's reacting, it's generating oxygen gas. So originally this started off with nothing, but as the oxygen gas is accumulating, it pushes the water level down. And then above this, then we have oxygen. But since we're doing this reaction in water, we have the vapor pressure of water above that. So when we do this, it wants to know, so we're looking for the mass of oxygen. So we need the mass of O2. And what do we know? We know that this volume is 1.02 liters. We know the total pressure is 755.2 millimeters of mercury. And the temperature is 293 Kelvin, which is 20 degrees Celsius. Okay, and we know that there's water there. So we need the pressure. So same idea what we did with the mass of argon. We need the pressure. We need the pressure of argon. We need the pressure of oxygen. This is the total pressure minus the pressure of the water. So we got to take out the vapor pressure of water. So this is going to be 755.2 minus the pressure of water. And from the chart, it's 17.55. So 17.6. And let's see here, subtracting that. This is going to be, I don't feel like doing math in my head today. 755.2 minus 17.6. This is 737.6 millimeters of mercury. So then the good old PV equals nRT. N is PV over RT. So we're figuring out the number of moles of oxygen. So our pressure, 737.6 millimeters of mercury. Atmosphere to 760. Conversions will be given to you. How many liters? 1.02. 1.02 liters. All over R, 0.08206. Liter atmosphere mole Kelvin. And this is 293. Is that right? Yeah. So put that in our handy dandy calculators. 737.6. Aren't you glad that we're not in the 1960s though? We have to use a slide rule for this. Times 1.02. So this is 0.04117, and then 0.04117 times 32 grams O2 per mole O2, and we get 1.32 grams of oxygen. How many sig figs we've got? 3. Okay. All right. So recap with this one. Oxygen over water. 1.02 liters of gas, oxygen, gas, and water. Total pressure, 755.2 millimeters of mercury. Temperature, 293 Kelvin, 20 degrees Celsius. So in this mixture, we have oxygen and water. So we know the total pressure. We got to figure out how much the partial pressure of oxygen is the total pressure minus the vapor pressure. Then we take that. So using ideal gas law, PV equals nRT, solve for N, PV over RT. Put in the pressure times the volume over RT. Then we get the number of moles. Number of moles times the molecular weight of oxygen gives us the mass of oxygen. So, questions with this? So why do we care? If we're going to do deep space travel, we got to generate our own oxygen. So right now we have nuclear submarines and they're underwater for a long time, but water is 89% oxygen, and they can just crack water. So we get all the oxygen that the sailors need to breathe down underwater. Aquanaut is easy to breathe when you're an aquanaut, as long as you have a lot of electricity. So if you're going to Mars, though, that's going to be a problem. You got to generate your own oxygen, and you also have to generate your own food. And what's a good way that you can generate both food and oxygen? Algae. Yep, so we got to feed and breathe our astronauts. And that's how we're going to do it, probably. Questions with this? All right, methanol. So now we're going to have gases and chemical reactions. And this is kind of also how the old school chemical engineers used to walk around chemical plants and turn knobs and get things to work properly. We don't do this anymore. We have computers that do everything. But the idea when you had a reaction vessel, though, you would have things in typically a reaction vessel. You had a big vessel, and you had inputs into the vessel, and then you had outputs somewhere. A lot of times you can have the product come out the bottom or something, and then you can take it somewhere. Methanol's got a lower boiling point, so if you compress it down, you can liquefy it. So that's typically what you do, and then you have a recycle that goes back in. Anyways, so the idea, you're making stuff in a gas chamber. So we have carbon monoxide plus 2 hydrogens makes methanol. And what volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 millimeters of mercury is needed to synthesize 35.7 grams of methanol? Okay, so looking at this, we have an input. We're inputting hydrogen where we want to know the amount of reactants needed to make 35.7 grams of methanol, so the product. So by dimensional analysis, how are we going to start? We can start with methanol, and then we can figure out the moles of methanol. We have the mass of methanol, we figure out the moles of methanol. From the moles of methanol, we can figure out the moles of hydrogen that we need. And then when we have the moles of hydrogen we need, we can use the ideal gas law to get the volume. So it's combining now we're taking the stuff from chapter 5 and we're combining it with the stuff from chapter 6. So let's go ahead and do this. 35.7 grams of methanol. MEOH. Me is methanol, OH is alcohol. So let's see here. Carbon's 12 plus oxygen is 16. Hydrogen is 4. That's 32. So this is mole methanol over 32 grams methanol. And then we have 2 moles hydrogen to every mole methanol. Methanol is also known as wood alcohol, if you're wondering. If you're a wood alcohol, it's methanol. Okay, so that'll be 35.7 divided by 16. 35.7 divided by 16 gives us 2.23 moles hydrogen. And now we want to know volume. So PV equals nRT. I mean volume. Volume is nRT over P is 2.23 moles hydrogen. R is 0.08206 liter atmosphere over mole Kelvin times temperature 355 Kelvin all over pressure 738 millimeters of mercury times atmosphere over 760. So keep track of your fractions. And when I put this in my calculator, I think what I'm going to do is I'm going to multiply by 760 on the top. Because if you have 1 divided by 1 divided by x, that's x. Right, so because I'm dividing by 760 in the bottom, so in the denominator I have a 1 over 760. An easy way to do it is to bring it up top. So if you have a hard time doing that, just put parentheses around everything. So let me 0.08206 times 355 times 760 divided by 738. And getting that is 66.9 liters. Okay. So this problem here, we're combining the stuff from Chapter 5 and we're applying it to Chapter 6. So it's another reason why people hate chemistry, because you can't forget anything. It all is called scaffolding. What you learned before is scaffolding for the next level. So like when you have scaffolding on a building, if you take away the lower levels, then the whole scaffold falls, right? So you have to continue on to have all this knowledge. So, okay. We were going to make 35.7 grams of methanol, and we want to know the volume of hydrogen gas. Why do we care about this? Because if you're in charge of a chemical plant, and that's what you're buying for your raw material. So if you're a purchaser for a chemical plant and we're making this much product and this is our raw material, you have to be able to know how much raw materials you want to have to keep things going, right? So you'll probably have to bug a chemist if you're not familiar with this, right? But maybe you are a purchaser that knows a lot, or you're a plant manager. So then you should probably know everything. Okay, so we have 35.7 grams of product and backtracking. So from that amount of product, using the molecular weights and then the stoichiometric ratio between the balanced chemical equation, you can figure out the number of moles of product, or I'm sorry, moles of reactant that you need. So with 35.7 grams of product, we need 2.23 moles of reactants. And then using the ideal gas law, we can go back to figure out the volume, because that's what we store the stuff as, in volume of hydrogen. And then using the ideal gas law, we get 66.9 liters of reactant for this much product. Questions with this? Okay, so another thing with this, little bit of history, the carbon monoxide and hydrogen in this ratio, this is known as syngas, also known as town gas. So we don't really worry about this too much in Hawaii, but everywhere else in the country, we typically have heaters. And they used to use town gas to heat homes. So what is a problem with that, do you think, of using this mixture? It is explosive. So is natural gas. And the problem is carbon monoxide. It's an odorless, poisonous gas. Right? So a lot of people died. So we switched to methane. And but also syngas, synthesis gas, syngas, in this 1:2 ratio, this can be used to make basically any hydrocarbon. So when people, sometimes you see, this hasn't been on the news for a while, but sometimes you see things, we're already at peak oil, we're not going to have, what's going to happen, these kind of things. The truth of the matter is we don't need petroleum. We have the technology to not use petroleum. We've had this technology since about 1920. You can use synthesis gas. If you use an iron or chromium catalyst, you can make, it makes really good diesel and jet fuel. It doesn't make gasoline. It doesn't make very good gasoline. So it makes great diesel and great jet fuel. And so why do we care? Well, historical figure, maybe you've heard of him before, Adolf Hitler. He actually ran his war machine off of alternative fuels, what we consider today to be alternative fuels. So Germany doesn't have that much oil, but it has lots of coal and natural gas. So if you react natural gas with water, you get synthesis gas and carbon dioxide. Or it depends on you can get synthesis gas from methane, from steam. Steam and methane can make synthesis gas. And then Hitler made a bunch of diesel fuel. And if you know some things about history as well, the German tanks, the Tiger tanks, they were diesel powered. The American tanks, they were gasoline powered. So there were a couple advantages. The diesel is better because the American tanks, the high octane fuel, they can blow up much more easily. So the lower octane, the diesel fuel is much better for tanks. It's also one of the big reasons for the German push into Russia. They were originally going to go for the oil fields south of a city called Stalingrad, and instead, that was the original objective, is to go for the oil fields there. But then Hitler turned north and then invaded Stalingrad because it had the name Stalin. And he thought if he defeated Stalingrad, he could kill the Russians more out. But that wasn't the thing. They're looking for the fuel. But okay, let's go forward in history to around the year 1970. South Africa was engaging in these series of laws called the apartheid. And it basically was segregation laws. And the world said, all right, okay, South Africa, we don't like your apartheid laws. We're going to embargo you. Okay, so no more oil for you, South Africa. South Africa's response was, screw you. We know about the way of making alternative fuels, and we've got lots of coal, we got lots of natural gas. We're just going to make our own fuel and live happily ever after. And I mean, apartheid has fallen, of course, but there is a company in South Africa called Sasol, S-A-S-O-L, and they make synthetic fuels. And they're still in business. They make lots of money. Why do they make lots of money? We shouldn't talk about this, but the military uses it because synthetic fuels burn more cleanly. So the Royal Air Force has gone, or the RAF, they go out and say, hey, we use synthetic fuels in our jets because it has less soot. So the fuel that like commercial jets, that's petroleum based, and it creates a lot of soot. and soot's really easy to track on radar. So if you use synthetic fuels, it's harder to track your planes on radar. And I'm pretty sure we do the same thing in the United States, but we don't talk about it. So, but yeah, we can make our own. Why don't we make our own? So why don't we just switch from petroleum to synthetic fuels? A couple reasons. First of all is investment. We have trillions of dollars worth of infrastructure right now in gasoline and oil refineries. So we'd have to change that to synthetic fuels. It's easier to use petroleum. Petroleum is a liquid. You pump it from the ground and you throw it into a distillation column. Natural gas is a little easier to, well, petroleum's the easiest. Natural gas is a little harder because you have to compress it down, but it's still pretty easy. Coal's a pain because it's solid and you have to transport it in rails. Natural gas you can run in pipes. Petroleum you can run in pipes. But coal you have to run in boxes. Like if you ever gone to the mainland, you can see just trains of coal coming through. Just that, and so it's a solid. That's harder to work with, and it's dirty, so you have to wash it to get rid of the sulfur, and then you have to gasify it. So all these steps that where petroleum is thrown into a distillation column. Natural gas, you have to turn it into gas. You have to turn it into syngas. Coal, you have to gasify that from a solid. Solids are hard to deal with, and then this stuff, the synthesis gas, what the product that it makes really good diesel and jet fuel. And we have a bunch of cars that run on gasoline. So we'd have to switch to diesel. So, which is not that bad. But I mean, the thing is we have all this investment into it. But it also burns more cleanly and more efficiently. So, but it takes more energy. It's easier, like I said, it's easier to use petroleum. That's why we haven't changed. All right. And let's go on and talk about, let's try and do some problems. Airbag volume is 11.8 liters. How much sodium azide is needed for an airbag to fill? So how much sodium azide do you need to fill that airbag? If you've ever been into a car accident before, I've been in one where the airbag deployed. And what an airbag is, you have sodium azide. It's a powder. It's a really explosive powder. If you touch it, it explodes. So it turns from NaN3 to sodium and nitrogen. So you have a little packet of sodium azide, and then if there's an impact, then that sodium azide explodes and fills up an airbag, a cushion full of nitrogen gas. Of course, it also makes sodium metal. Airbags have lots of problems. So when I was in the car accident, I had my seatbelt on. It didn't even, and also I got long arms, so I didn't even hit the airbag. But when it sprays out, among other things, it sprays out sodium metal, which turns to sodium oxide in the air. And I got a chemical burn on my arm, where my steering wheel was, and I got a caustic burn on my arm from that. Problem with some people also is that again, your eyes can blind you. You can breathe in the sodium powder, and that can cause what's called pulmonary edema, which means fluid in your lungs. So airbags, it's amazing. If a company came up with this, they would probably be sued, but it's government mandated. So airbags can be very dangerous. Okay, but either way, from the impact, they can expand very quickly and form a cushion. So, but the airbag volume is 11.8 liters. How much azide is needed for the airbag to fill? And I'll try and simplify this for you. So NaN3, so 23 plus times 3. This is going to be the grams per mole NaN3. And we have 11.8 liters. we need mass. So similar to the methanol problem, we need to know the mass of a reactant given the product. In this case, the product is the volume of air. The airbag, and what's the, okay, so obviously there's the ideal gas law. Is this, what's the gas here? It's nitrogen. The airbag fills with gas. Nitrogen is what it fills with. So we know that that airbag's going to be at 11.8 liters at ambient pressure and 0 Celsius, 273 Kelvin. How much azide do you need to fill that up? So if you're a car manufacturer and you want to know how much sodium azide. So 14 times 3, that's 12, that's 42 plus 20, that's 65. Make that easier for you. I guess I'll give you R. Keep on forgetting you guys want to memorize all these things. So I'm labeling A 12 grams, everything B 23 grams, everything C 27, everything D 65. Okay, so who's stuck? Okay, all right. Go ahead and start talking. Pressure is one. Pressure is 1 atmosphere. People are asking. Formula. the line. Are you following? Are you following? Or? So now that you have the volume of nitrogen, or the moles of nitrogen, so you have this equation here. So the number of moles, and it's a 2 to 3 ratio, and that's this dimensional analysis. That's 65 grams per mole.
Unit and 08206 for temperature.
Yeah.
Okay.
So you understand this PV equals nRT, I'm solving for n, which is PV over RT.
Yeah, but what I'm having trouble with is getting things to cancel out.
This should be in, okay, you
Did
solve for the
I
n.
reverse them?
PV over RT.
1 atmosphere. So
That's 11.8.
Uh-huh.
Okay, okay, if you do all that, then that's going to be, this whole thing is going to be moles of nitrogen.
Right.
Okay, then you have moles of nitrogen times 2 moles over 3 moles of nitrogen, so the moles of nitrogen cancel.
Oh, so then that'll cancel it out.
Yeah.
Okay.
And then you get moles of azide, and then moles of azide over 64
That'll
grams.
cancel it out.
Yeah.
So what I'm going to end up with is the product of this times 2 times 65
Divided by 3.
divided by, okay. Okay. I think I know what
Okay, good.
I'm doing. Thank you.
Yeah. The alarm is about to go off. Answer is 22.8. And
So B.
so PV equals nRT, N is PV over RT. So 1 atmosphere, 11.8 liters over R times temperature, we get a half a mole. So then from the balanced chemical equation, it's 2 moles sodium azide to 3 moles nitrogen. And then sodium azide is 65 grams per mole. And then so this is going to be 22.8 grams NaN3 is the final answer. Sorry I didn't get to this side of the classroom here. But does anybody have any quick questions before my alarm goes off? And nope. Okay. Alrighty. Have a nice rest of your day then.